All right, welcome everyone. This is the grading spectrometry lab. We're going to be dealing with the spectrometer here. What is a really lovely piece of equipment. I really like to play with this thing. No digital readouts, no electronic, nothing, just old-fashioned arc measurements and a nice vernier scale. Really lovely piece of equipment. What we're going to be doing is looking at the emission lines of different types of gases. Now the tube here is filled with hydrogen gas, and the power supply is now passing an electric arc through it. This is ionizing atoms in the gas, and then they're recombining with the electrons and the protons coming together. As they do that, the electrons cascade through the different energy levels and put out all the possible wavelengths of light that you can between any two arbitrary energy levels of hydrogen. We'll be using this to look at the emission spectrum of hydrogen in the visible band. We will use that information to calibrate the device, and then we will be using the calibrated device to look at the wavelengths of helium and mercury emission. Now let's take a look at the spectrometer itself. It's a very nice piece of equipment, very laboratory grade. There is a tube here that I've got pointing towards the emission tube, and that tube at the very end of it has a little slit. So I'm going to orient straight up and down. That allows light to pass through that tube. That light is going to come in here, and this small square object with the circular window is a diffraction grating. Okay, and we've studied about how diffraction gratings work. The light from the diffraction grating is then going to go through this tube to where I can observe what's coming out of the diffraction grating at the end. Now, the way diffraction gratings work, a lot of light goes straight through in the central maximum at n equals 0, but then a lot of light is angled off at n equals 1 to the first order diffraction. Now, you've all done problems where you've figured out that there is a difference in angle between red and blue light coming out of the grating. What we want to do, we can figure out from the theory of hydrogen what wavelengths are coming out in the visible band. We can then observe which angles we see these rays of light at, and from that figure out the spacing on this grating. Right? It's supposed to be a 600 line per millimeter grating. We're going to find out what it exactly is so that we can accurately measure the wavelengths of the other samples where we don't know what wavelengths are coming out of the discharge tube. Okay. To start, and then the device has a circular rule. I'm going to try and keep this where the phone is in focus. There's a circular rule to tell you exactly what angle the top tube is pointed at, so you can figure out what angle you're looking at when you find an emission line. Okay. And to get started, these two tubes are pretty much straight together, but the zero reading on here is at 300 and something, and it should be reading at 0. So I need to line up the equipment properly at the start. I'm going to position the tube so it's looking straight at the discharge, and then I'm going to look through the eyepiece of the movable tube until I can just see the 0th order light coming through the grating and going straight. So now these two tubes are aligned perfectly, one with the other. if I loosen the connection between the arc template and the tube, then I can adjust the 0 point so that it reads exactly 0 degrees at this point where I'm looking at the central maximum. Okay. Now, if you haven't already done so, well, obviously by now you should have read the procedure for the lab, so you know I'm skipping something. If you haven't already done so, I would recommend that you go fill out Table 1. In Table 1, we're doing a calculation very similar to what you're doing in the homework. You're figuring out the energy of an M state and an N state, and turning that into a change of energy as the electron cascades through those two states to predict the emitted wavelength that we have in the 6 to 2, the 5 to 2, the 4 to 2, and the 3 to 2 transition. Those 4 lines to the second excited state, well, actually the first excited state, the N equals 2 state. Those are the only ones that show up in the visible. The N equals 1 state is down in the ultraviolet. The N equals 3 state is up in the infrared. It's the N equals 2 state, what's called the Balmer series, that is observable in the visible. Now we want to look for a red, kind of a teal colored, and a blue line. You can usually only see those first 3 lines in the spectrometer. We're going to do that 3 times to get a good average theta for those lines, and then take the sine of that angle to use in the table below. Okay, so what I need to do now, I'm going to place the cover over the diffraction grating. This keeps out stray light and makes it a little easier to observe. So now I'm going to look for the positions of the red, the teal, and the blue lines. Okay. I'm not sure if I can do this in full light. I wanted to show you all of the equipment in full light. Let me dim the lights. And now this should be enough to be able to see the lines. Okay, so now I'm going to look through the tube, and I'm going to scan slowly to one side, looking for the first order emission line. And there we go. Okay. Don't know if I can show you this, but yeah, right there. There's a nice fat red line right in the middle of the crosshairs. And when I look at the scale, we are, just a second. I need more light. Okay, we are just between 23 and 24. I can use the vernier scale, which I've described before but never forced you to use, to read that off more accurately. I'm going to say that the 7th line of the vernier scale is lining up best. So that is going to be theta 1, 23.7. degrees. Okay, now I'm going to take the tube and scan back to the other lines I saw. Think this is it. There is, I don't know how well you can see it, but there is a nice green line there, and that is it. It's between 18 and 19, almost 19, reading the vernier scale. We call that 18.4 degrees. I'm going to go back to the tube, turn it to the nice blue line, read off the angle, which is not changed by a lot. It is 17.3 degrees. Now we're to do this 3 times. Normally I would make you do this with 3 different lab partners so that everybody got a chance to do it. I'm going to move the tube offline and then go back . Find that blue line. It's a little bit different. I'm going to say that blue line is at 17.3. Oh, well, that was the one I said before. 17.3. These are brand new tubes I bought this year. They're working out really, really well. Back to the equipment. I turn slightly to get that green line in there, nice green line. We are now at looks like 18.8 degrees. A little bit different from before. And now I slide over to the red line. 23.7. Oh, and that's the same as what we got before. Okay. Yeah, what the heck, one more time. Slide the tube way over. I'm going to slide it back. And look for those emission lines again. Wait, I'm looking for, is it that one? Yeah, it's that one. Looking at, let's say 17.1 degrees. And then go over to the green line. A little bit harder to see as this warms up, not sure why. Which looks like it is at 19.1. And then finally, a strong red line at 23.4. So, there we have it. Okay, you're going to take those, you're going to get sine theta, transfer those down to the next table, use that, using this equation you can figure out the, from table 1, you're going to take the emitted wavelength for the red, the teal, and the blue lines. And then from that, you're going to calculate the grading spacing using the appropriate equation. The grading spacing, you're going to average up to get a best value. Okay. I like to keep these videos short. Let me stop this one and then go on with the second one in a moment.